ladies and gentlemen. So in case you're wondering, the white and grayish, sort of silvery, blackish, whatever color that is, this is Boomer. See? Now you see Boomer. See, Boomer's not a figment of my imagination. Ain't that right, Boomsy? Oh, that was my wife, by the way. And this is Monkey over here on my left arm. Yeah, Monkey, yeah, I know it's a dog. However, my grandson didn't. So when the wife brought Monkey home, the grandson thought the dog was a monkey and was like excited it was a monkey. So it was like, okay, guess the dog's name is going to be Monkey. So I called her Monkey Butt because a deal like that. Look at her butt. Well, can't see it in the video, but she has kind of a, well, it's not even more. She looks like a baboon when she's going through her monkey, or what is it called? Puppy uglies. Yeah, so I'm going to put Monkey down, and now you see Boomer. It's hot right now, so I'm going to take Boomer. I'm going to put him down. See? Hey, say hi to everybody, Booms. Say hi. Just say hi. Do you say hi? Can you say hi? No, don't look at me, Boomer. Go look at that. Go look at that. Ain't that right, Boomsy? The Boomsy got it? Okay. Alright, well, now this is Boomer's ball. Oh, here it is. Wait, where did it go? Ah, there we go. This is Boomer's ball. This is Earth. So, Earth flies like that. An American football. It's not shaped like an American football, but it flies like one. So here's the North Pole. Here's the South Pole. This is its galactic flight posture. A galactic plane, basically right around in here. Hang on, Booms, hang on. Just wait just a second. And it spins like this. And it also has a wobble, or a precession. That's how Earth works in flight. Okay, here you go, Booms. Okay, now that we got that out of the way, it's just a reminder. Oh, by the way, go ahead and be sure to like the videos, even though I'm not the greatest entertainer out there. And I'm picking the Boomer fur off my desk because it's just covered in boomy furs. So anyway, like it and subscribe. So I'm going to go down here, jump right in. This is my PowerPoint by death for today, ladies and gentlemen. And this is probably going to be my, excuse me, my conclusion on the South China Sea Impactor. So last night I went back to the South China Sea impact site to see if I couldn't find, well, I already found it, what I suspected to be the blast ring number 1. And in order for me to determine the size of a meteor and its diameter, I have to find blast ring number 1. Some of these guys have several blast rings, and you can sit there and like map them constantly. And others, you're just like, you're lucky if you get 1, but you usually get 2, and and your second one is at least the very broad, huge blast ring that basically gives you the full spectrum of that entire, you know, I would call it astroclastic cloud. Yeah, so anyway, I went there and I looked at it, and you know, when you take Google Earth and you zoom in, you zoom out, a lot of the times when I'm looking for things, I'll find the circle. I look for the circles first. I know scientists are like, that's ridiculous. You don't look for the circles. Are you sure it's not a volcano? It's like, yeah, I'm quite certain the circle I found isn't a volcano, especially when it's like, you know, anywhere from 1.2 million meters in radius. That's not even diameter, ladies and gentlemen. Radius. Yeah, that's not a volcano. Come on now. So anyway, I look for the rings, and then if I can't, well, usually when you do the circle in Google Earth, it has a line that goes to the left. So I take, while that's still live in the color yellow, I go and I grab my little pin and I go boop right smack on the center of that circle, and then I go zoom in all the way close until I have a good idea of what I can examine there. Do understand, I don't always find what I think I might be looking for. There are these footprints and these signatures, but they're not everywhere. And there's times when I don't find anything. I'm just like, well, it kind of looked like something, but just not seeing the footprint. And when I say footprint, I'm talking about the blast bow wave, the B2W, and basically the pop. Those are the two key elements I'm searching for once I've already found the cycle. Ain't that right, Boomsy? See, he turned around, he paid attention to me because he knows I'm talking to him. He knows that his opinion is very important here. Okay, so here we are. We went back, and I was going in at a different elevation above the earth at this point, and then I saw it. So this blast bow wave here appeared to be more prominent than the other one. I'm not saying the other one isn't necessarily a blast bow wave as broad as it was, but if it was a blast bow wave, it didn't impact at the same time that this one did. And the reason I'm saying that is because if it's broad, its trajectory is going to be closer to perpendicular, so it's going to be an extraordinarily high angle. And then it also means that as we've seen in my other PowerPoint presentations, the poo, or the back azimuth to where that origin was, is off. In fact, the variance between South China Sea and the North Pacific Oceanic Impactor was 44 degrees. Now, it is less than 44 degrees, and not only that, but as I noticed this blast bow wave here, you'll pay attention here, my poo is right smack up these lines. And when I was first looking at it, that was kind of what I was looking for, but for some reason at the elevation that I was viewing it, I wasn't able to actually see what I might consider to be a blast bow wave. And when I recognized this particular one last night, I'm like, bam, I've got it. Well, here it is. So after re-examining the South China Sea Impactor's B2W, I discovered that the second B2W aligns the poo with the Spratly Islands. Okay. It wasn't until after I wrote that I Googled Spratly Islands, and then it was like, oh wait, they're kind of further east. I thought all these islands were the Spratly Islands, but whatever, my bad, I don't care. These islands right here, you see it says South China Sea Pop? Yeah, right there, those islands. Anywho, so I didn't change that because, like me, if I were to give people some kind of name of this particular alignment and linear group of islands, they're not going to know any more about where in the world those islands are than I would. So, yeah, Spratly is like, oh, Spratly Islands? Oh, yeah! Everybody knows where that is. Okay. All right. Just like I was talking to a fella. Never mind. Okay. Yeah, I probably shouldn't say anything. Okay. My bad. I know. Suspense, right? So this poo is most likely correct at a BA of 5.38 degrees. BA is back azimuth. So, for those of us who are not so familiar with land navigation, an azimuth is the direction in degrees or in mils that we read on a magnetic compass. I say two graduated scales in circumference. Degrees, mils. So for those of us who are civilianish, and we don't really know the materiary-ish, okay, 360 degrees in a circle, civilian. All right, so there are 6,400 mils in a circle, which are military. How do you like that? You like that? Yeah, put a little spin on it. I didn't say it quite right that time. Military, yeah, like that. Okay, military. So anyway, there's 6,400 mils in a circle, which breaks down to 17.4 mils per degree. And the reason that is because when you're using basically laser rangefinders, that type of thing, right? If you know a distance to be 1,000 meters, then at every 1,000 meters, one tick mark represents 10 mils, but at 1,000 meters, that 10 mils becomes 100 meters in deviation, or 100 meters from left to right. At 2,000 meters distance from your location, those 2 tick marks in mils of 10 mils now represent a deviation of 200 meters, so on and so forth, as it graduates to each greater or each higher number of 1,000 meters distance from your location. So, excuse me, it helps you to determine where things are on the planet's surface. So anyway, the back azimuth, when we're using these compasses, right, is, so you basically, the direction that something comes to us in is one point of view, and we'll say that that is the primary direction. But if we want to know the direction, the opposite direction of where something came from, not where it's going, not its heading, we want to know where it came from, point of origin, poo, then we want to read a back azimuth, or take that heading and either add or subtract 180 degrees depending on where on the compass that heading degree is. So it's called LARS or RALS, right add, left subtract, left add, right subtract. You can always talk to somebody who knows what they're doing with stuff like that if you want more details on it. A difference of 16.43 degree variance rather than a 44 degree variance in comparison to the North Pacific Oceanic Impactor poo. That's what I was telling you. So now, instead of having a poo off over here and a poo off over here, the poos are kind of like that. So that tells us something. That tells us that these 2 world-class impactors, 2 of probably only 4, because I've only found what I believe to be evidence of 4 world-class impactors, these 2 practically came from the same place. That's my point. My point is, same place. I can't tell you what the trajectory of the North Pacific Oceanic Impactor is, because I totally have nothing visible there any longer to give me the first blast ring. So all I can do, you have to have 2 things. You have to have the blast bow wave, and you have to have the first blast ring. Without those 2 elements, you cannot accurately determine the trajectory of that particular impactor. All right? So we're going to come down here, because this video here is going to basically show you, and the scientific community, this is how you can find out where these rocks that fly in space are really coming from. Okay, we see a lot of rocks fly around our planet. Maybe they come from, those do come from our solar system. But yeah, we might be looking in the wrong place, because there's far more. Space is pretty large out there, you know, like military combat pilots will tell you. Little sky, big bullet. So little outer space, big rock. The same thing, right? If you're flying there, it's going to find you, and it's going to come from just about anywhere. It doesn't just come from a set place. We get slammed in the front, boom, butt on the windshield. We get hit in the butt, wham. You were standing in the way when the racquetball went forward and you didn't move. That's your fault. Got you right in the back, right there, right square in the back with that little rubber ball. All right, and or then you do, oh hey, it's coming around, woo. Okay, came around from our solar system, so it spun around the Earth a couple times before it went and clobbered us. I'm just saying, I don't know. Anyway, I do know this impactor right here, ladies and gentlemen, did not come from our solar system. And I'm going to show you why. Alright, so this impactor's approach was borderline high angle, low angle. The narrow B2W wingspan, as we see right here from left green to right green, is nearly at the point of becoming an inverse impact crater. which is indicative of a low angle trajectory. So here it is, ladies and gentlemen. You got that little badminton birdie shape going like this, right? And when my arms are wide apart like this, like almost 45 degrees apart from each other, and that's about your average relative sort of wingspan, right? On your wingtips of your B2Ws. But if I bring those in closer, the round's trajectory is becoming lower and lower. And when it gets to a certain point, it goes bloop and flips. When it flips, it blows the matter. When it strikes, it blows the matter forward. When it's high angle and hits like this, bam, it blows the matter rearward. Okay? We tracking that? So when it's low angle, boop. And if it's really low angle, it'll go boop, 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 boop. And it'll slide all over the place. Yeah, it makes that sound too. I guarantee it. So anyway, here we are, right? Now we talked about the trajectory being low angle. So what it boils down to is I'm going to read to you right here. Though the trajectory is 55 degrees from 0 degrees. Now I was telling you before, in the artillery, 0 is at the top. When we give you an attitude to something, attitude is any direction that falls within 0 to 3200 mils or 0 to 180 degrees. And it's I'm sitting here showing you as I'm looking at it. This is how you're looking at it. 0, 180. It goes here. The attitude is always and only given on this side of the compass. Why? Because you don't give people two readings, right? You only need this half of it to give you an idea where that line goes. All right, so anyhow, you're talking about a 55 degree trajectory from 0. So that means when 0 is up here, I'm going from your point of view, I'm going to drop that angle to 55 degrees right here. So now, in terms of Earth, when we're standing on the ground and we talk about trajectory, we don't talk about the trajectory as we perceive that trajectory from the 0 degrees. We talk about the trajectory in relation to the ground on the Earth, the ground being basically our horizontal zone, right? So when you want to figure that out, the approach, so the impactor is coming in like this, and it had a trajectory of 55 degrees as I'm explaining it here, but its approach above the ground was only 35 degrees. And that tells us that it was only like 5 degrees above the highest pitch of a low angle trajectory, okay? Being like 30 degrees. When you start hitting 30 degrees, you're talking about things that don't necessarily dig a hole. They kind of just go bam. You got it? Bam. Watch out. Watch out. Bam. That's all it goes. Or not. Yeah, 2 cars right there in the middle. All right, going down to the next one. Now, the reason I put this slide back in here, I have it in some... Doodle, I'm talking right now. Okay, I had it in another presentation that I've already shown. And anyway, I put it in here because I needed to refer back to the degrees when I was establishing at what the span or the variance had gone to from 44 to whatever it was. So that's why that's in there. Now I'm going to this one. So if we look at the planet with these two trajectories, or not trajectories, my bad, the poos going off here, you can see now they're even more oriented to a point of origin out here somewhere that is close, probably closer. Like, in fact, if you were to draw this line out 500 million light years and draw this one out 500 million light years, you might see the two lines intersect. If these two impactors originated from the same location, it's almost like triangulation. If I could find a third impact site in this area, certainly not of the same magnitude or the same mass, because if it were, it would be like screaming at you right there, and it isn't. So, I mean, you really have to look hard. But if I were to find more of these coming in from basically the same direction, then you could triangulate to the exact location or a near exact location to their point of origin. And when you're talking about going 500 million light years out there, whatever the distance, right, they could be 500 jillion light years apart from each other, but they could have come from the same, cloud of whatever, right? Nebula, whatever, who knows, right? Maybe from some place where we know there was a supernova. Anywho, there you got the idea there. Going down to the next one. Okay, now, this was the first blast ring that I had already determined could very possibly be a blast ring, but it didn't lie. It wasn't oriented where it should be oriented. You see right here with the blast ring going around, it appears to be evenly distributed in this zone right here in front of the bow, the B2W, the blast bow wave. And this is the blast bow wave right here, okay? That is a prime indicator of this being confirming that this is blast ring number 1 for that B2W. It wasn't, and I wasn't going to use it as a blast ring number 1 for the other B2W because I showed that it was coming out this way, much broader spray, if you want to call it that. And so it didn't quite fit my criteria. I know I keep dissing the scientists and their criteria. Well, I do have criteria too, and criteria is important. We just shouldn't create criteria that chokes us and prevents us from thinking logically. This is logical. It's a proven method. Very proven. So, y'all the scientists out there, if you don't believe me, go to an impact area and start looking at craters, because you obviously aren't familiar enough with what you're looking at or what you're looking for. Alright, so here we go. Now, meteor crater in Arizona is the basis and the control of my establishment or estimation of the actual diameter of meteors elsewhere. Asteroids, rocks, I don't care what you call it. I'm calling them meteors because it seems like most people are more familiar with meteors, and so you call it what people think of it as. That's why it's titled Meteor, Gemmel's Meteor Impact Atlas. Just keep it simple, right? KISS method. So here it is, right? So basically, you have the scientists said that the rock that blew up and made meteor crater was about 30 to 50 meters, not kilometers, meters in diameter. All right, and so I think in terms of metrics. So I'm sorry, when you're an artillerist, you got to go metric. So that's how it works, yo. So anyway, you basically take the radius of meteor crater, and which is about like 500 some odd friggity-doo meters, something like that, and then you find out, well, what is the comparison in size of the impactor that blew up, and we're going to give it the average, 40 meter diameter. Forget the 50, forget the 30. We're going to go in the middle. So that's what we're basing it on, and that means that meteor crater, based on the scientific research and analysis, would have been about 40 meters in diameter, it would have also been at that 40-meter diameter 7% the entire size of, or 7%, my bad, 7% the, I'm trying to think of it here, I'm getting tired, 7% the radius of the blast ring, and we were referring into the meteor crater hole, the border around its hole, the ridge, as the blast ring, right? It actually has quite a few other blast rings. That's right. That isn't it. It had a astroclastic cloud that went out quite a bit farther. I'll show it to you one of these days. Anyhow, 7% of this particular blast ring here, ladies and gentlemen, and this blast ring here is 212,417.25 meters in radius, and 7% of that is equal to 14.9 kilometers in diameter. So this impactor, I know that in my previous videos I stated that this impactor was at least 8.4 kilometers in diameter. And when I said that, I was basing it on the B2W. We know, I know as a fact, providing the details that we get from the scientific community on Meteor Crater, that the B2W is at least capable of giving us the minimum size, the least size, the smallest size that an impactor could have been. And then we always have about the same ratio in orientation and size. Not always, I mean, because always is a superlative, but almost always have that same ratio. And that's what I'm looking for when I'm looking at these meteor craters. I'm looking for that ratio. I'm looking for that footprint. All right. So, 14.9 kilo, and this basically, is just showing you my math. That way all you mathematician teachers out there can be like, hey, not bad. I forgot all the algebraic crap that you got to do. So it's sort of algebraic, but it's kind of like Gimel-raic instead. All right, so down here, I'm showing you how I'm doing it, right? So basically, we're looking at the radius here, and the radius here is 122,134.09 meters in radius of. So that's your distance from the pop to the B2W. So the pop from the B2W is 122.1 multiplied by 100 divided by 212.4 equals 57.5%. All right, what's 212? Boop. That guy. So basically what I'm telling... I know, puberty, right? So basically what I'm telling you is this circle here is 57.5% the size of this circle right here. We need to know that in order to do, if you look down here in the bottom left, you see the top of it. That's where we start to draw the little geometric things and make you, figure it all out, right? Like a compass. All right, so now once again I'm showing you my math here. What is the 4? Well, we got to go down here. Excuse me. So I draw a line down here. The big fat blue one down here is my pop to B2W distance and range. On my sheet of paper, each one of these squares is 1 square inch. So this line is 4 inches. Now I go back up here. Now that's why you see up here 4 inches multiplied by 100 divided by 57.5% equals, well, about 7. So if you take that 5 rounds the 9 up to 0, and the 1 carries over to 6, makes it 7. So we went with 7. So that means that if the pop to B2W range is 4 inches, then that means at 57.5% the size of the BR number 1, then the range of BR number 1, the pop to BR number 1, is 7 inches. So my little brown line comes out here from 0 to 7 inches. See how that works? And this direction is 270. I was playing with this last night and I got a little bit tired. I'm like, the PowerPoint was telling me that I moved this line up to here until it remains here at the pivotal point, and the 7th inch point or edge meets the vertical line of the pop to B2W range. So at the B2W range, you draw a line straight up, and then you pivot this line here like a compass until it reaches that. That is going to tell you what your trajectory is of that particular impactor that struck the earth when it hit. Alright? Alright. And this is where you get your 35 degrees. Alright, so now this is all my math. I'm not going to read it to you. I read it to someone else, but I'm not going to read it to you. You can read it if you want. Okay, you talked me into it. I'll read it to you. No, I won't. 55 degrees. I did this right here. Lars, remember I said is left add, right subtract. Okay, so when we take this line here and we move it over here, if you're looking at it in terms of clockwise or counterclockwise, we're rotating it clockwise. And because we're rotating it clockwise, in your view, clockwise goes this way. Check. So clockwise means we're moving that line to the right. Right add, left subtract is Rawls. Left add, right subtract is Lars. Whether or not you use Lars or you use Rawls depends on whether or not the directional degree you are adjusting from is either above 180 or below 180. If it's below 180, you add. If it's above 180, you subtract. Woohoo! Okay, now we're tracking. All right. Anyhow, next slide. I know, PowerPoint by death. I know. So basically, I put the South China Sea way the hell up here on what appears to be the top of the planet. No, I'm not saying that's the top of the planet. I just put it up there top dead center, so that we could get a perspective on just exactly what a 55-degree trajectory, or in this case a 35-degree approach, would appear like as it struck the earth. And that's what we have right here. And the vertical angle is 35 degrees. Why did I refer to it as a vertical angle and not an approach? Because if you're standing right here where the point is on the pop and you're looking out into the sky, you're going to look across, let's say for instance you're looking across from yourself, eye-to-eye contact to your great big buddy right there, right? And the two of you can see eye-to-eye because you're like on the same level. Well, that's the level that you're going to raise from is your elevation. Elevation is what you're standing on. You're going to raise to a vertical angle of, from that elevation, 35 degrees. So your vertical angle and your approach are one and the same. But when you're out making an observation, it's a vertical angle. You don't observe the approach because the approach already took place quite possibly several million years ago, if not a billion years ago. What we do know when we're looking at this stuff right here, I'll show you back up here. Was it this one? Yeah. What we do know about this is, if you look over here on the North Pole, if you take the Jupiterian stripes that this guy created and the Jupiterian stripes that this guy created, it puts the North Pole within just a few degrees difference from each other. That's why I'm telling folks, not only that, that's not only the reason why they happen very close to each other in sort of a cosmological sense of time, but because not only did they happen so close that the North Pole was very close in orientation to itself as to what it is today, but both of them gave us 9 Jupiterian stripes scores. The other 2 world-class impactors gave us 2 different numbers of Jupiterian scores. So we currently live in what I refer to as our present stage in life, which is the Jupiterian 9-stripe period. So if you look at the sun, NASA already figured that one out, and they just don't even know it. It's going to have its 9 stripes. You look at Jupiter, you have 9 stripes. Guarantee you look at all those other planets closely enough, you're going to find 9 stripes. 9 stripes gives you the speed of rotation. Now see, this is where physics kind of leaves me behind in this sense. You have the same rate of rotation because the rate of rotation is 9 Jupiterian stripes. The more stripes you have, the faster the rate of rotation. However, that doesn't explain how we, as we visually look at planets and things, their winds are being measured to be rotating very quickly, right? So that's one of those things where the real specialist sort of people can figure that one out. I'm the artillerist. I can tell you where it blew up. Well, anyway, so I do have a lot of theories out there, working theories on, the universe, the galaxy, the cosmos. I call the cosmos larger than the universe. I'm sure you'll find it very interesting if I don't bore you to tears. Okay, so I was boring myself to tears the other day when I was listening to myself. Oh my God, dude, get to the point. You're killing me. Oh, wait a minute, that's me. Okay, anyhow, I just mentioned it. The Jupiterian 9-stripe period. These 2 guys happened at about the same time. This one is the most recent because this one occurred with the North Pole in its current location. So the Jupiterian stripes that I show as the most prominent in the Pacific Ocean are telling us that when this bugger clobbered us over here, it just happened. And it's probably what happened to, Scientific Atom and not them two. Everybody they knew. So they, back in the day when Scientific Atom and Scientific Eve were alive, and all the other peoples were alive, they were like the Joneses. And then, bam! South China Sea impactor struck the Earth and all hell broke loose. Earth started to melt. And the only survivors, oddly, were Scientific Eve and Scientific Atom. And so we're not able to find the missing link. Well, maybe it's because the missing link got melted away. Who knows, right? I don't know. Just things to ponder. All right, going back down here. All right, now I was back down here and all my trajectory cap. I told you about Lars. Next guy. I showed you this dude right here. All right, then we come down to my summary. Now, whoever you are, scientist or otherwise, go to the Union Reef. That's this reef right here, okay? All right, so if we go back, I know. Union Reef, that's Union Reef right here. So you get a better idea when you're looking at Google Earth right there, right? You get Union Reef. And these are all the islands that are smack dab top dead center of that approach. That's what I was looking for all along. It just took me a while to find it. All right. Now, go to the Union Reef at the South China Sea Impactor's POP, point of penetration. Look in the direction of the poo at 5.38 degrees and a vertical angle of 35 degrees above your elevation. Follow the skies as the Earth rotates one full revolution. Identify all nominated areas of interest, NAIs, that could potentially have been the SCSI's actual point of origin, or POO. Oh, and I guess these are not the Spratly Islands. Haha, my bad. Alright, that's it, folks, for this video. I'm going to let you go now. This is my second time doing it because I had to do a special video for someone else. But I'm not airing that one. So this one's for everybody else. Okay, it was nice to... Oh, wait a minute. It was not talking to you. Boomer says bye. Alright, don't forget to like and subscribe, right? I've got lots of stuff to share. Great stuff. There's a great big crater hole in Russia, too. And you know what's really funny? They're digging in it. They're actually digging in the pop. Go figure, right? I bet you that's where they found all the iridium. No kidding. All right. Anyway, there you go. See you guys later. Bye. See you tomorrow. Well, maybe not.